Hello, everyone. My name is Itsios, and I am a 5-year postdoctoral researcher at Humboldt University in Berlin. This talk is about the formations of nonlinear sigma models that preserve integrability and their relation to type 2 supergravity. The talk will be based on my recent work, which you can find in these two papers here at the bottom of the slide. And at this point, allow me to switch off the camera in order to maximize the space on my screen. Let me start with the plan of the talk. The plan of the talk is as follows. I will start with an introduction to the lambda model on which this talk is based. And I will also pose the main questions that I would like to address. Next, I will focus on the interplay between the lambda deformations and 10-dimensional supergravity by presenting two new supersymmetric solutions of the type 2 supergravity, which correspond to the embeddings of lambda models based on the groups SL2R and SU2. Finally, I will summarize and discuss future directions. In the past few years, there has been a lot of interest in studying the formations of two-dimensional nonlinear sigma models that preserve integrability. A notable example of such deformations is the so-called lambda model, which was introduced by Itsios back 2013. This model describes an integrable deformation of a CFT and interpolates between a Vezo-Minowitten model and the non-abelian dual of the principal current model. Having said this, the building blocks of lambda deformations are the Vezo-Minowitten model on the element little g here of some group which I denote with a capital G, and the principal chiral model evaluated on an element G tilde, which belongs to the same group. Starting with the sum of the Vezo-Minowitten action and the action of the principal chiral model, a gauging procedure similar to the one that Boucher followed for T-duality results to a sigma model with this action here in the box. This is the action for the lambda model, which now depends only on the group element G and not on G tilde, which we have gauged fixed to the identity. As you can see from this expression, the lambda model is given by a Vezo-Minowitten model shifted by this term here in blue. And the blue term describes the deformation, and it is written in terms of the currents J plus and J minus. Also an orthogonal matrix D that is given by the adjoint action of the group. And with TA here inside the currents, I mean the generators of the group. And also K refers to the Vezo-Minowitten level. Now, the deformation, which gives its name to the model, is denoted by the letter lambda, and it's a constant matrix. And in the rest of the talk, I will restrict to deformations that are proportional to the identity matrix. Let me now mention some properties of the model. The first one is a kind of weak, strong coupling symmetry, which is realized at the level of the action by sending the group element G to its inverse, inverting also the deformation parameter lambda, and also flipping the sign of the Vezo-Minowitten level K. The second property is that the lambda model is classically integrable, which means that its equations of motion can be expressed in terms of a lax connection, which allows us for the construction of infinitely many conserved charges. The lax connection is denoted here by L plus minus and is written in terms of the currents J plus minus. The deformation also depends on the deformation parameter lambda, the Vezo-Minowitten level K, the matrix D, and the complex parameter Z, which plays the role of the spectral parameter. Of course, when lambda equals 0, we obtain the Vezo-Minowitten model. However, we expand the deformed action for small values of the parameter lambda and keep terms up to linear order in the expansion. we derive the non-abelian T-dual filling model, which has an action of this form here. This action is written in terms of a current perturbation of a CFT, where the two sets of currents, J plus and J minus, commute and satisfy the current algebra here. Moreover, the interaction triggers energy flow under which the target space metric and the symmetric field mu change, and this in turn translates to a flow for the coupling lambda, and the flow is expressed in terms of the one loop beta function, which takes this nice form here. Notice that mu denotes the energy scale, and Cg is the quadratic Casimir of the group in the adjoint representation. Also notice that the UV sits at lambda equals 0, which is the CFT point. There are two interesting limits that one can take. The first one is when lambda approaches the identity. And in order for this limit to make sense, one has to expand both lambda and the group element for large values of the Vezo width and level according to this fashion here. It is crucial here that the subleading terms in both expansions are of order k to the -1. If we plug these expansions into the action of the lambda model and take k to infinity, then we arrive at the sigma model with an action of this form here at the bottom, at the top of the slide. And this is recognized as the action for the non-abelian T-dual of the principal chiral model with radius kappa. On the other hand, when lambda approaches -1, we can consider expansions of this form here, where now we expand lambda and k, where now the subleading terms in expansions of lambda and g are of order k to the -1/3. In this case, the sigma model action that we obtain corresponds to the action for the NAPI model. Let me now move to an example, which also will appear in the rest of the talk. The simplest non-trivial example of a lambda model is, of course, based on the SU2 group. And in order to construct it, all we need is a parameterization of the SU2 group element G. The choice we make here is in terms of an angle alpha and the unit vector n. This unit vector is defined on a two-sphere, which is parameterized by the angles beta and gamma. If we plug this group element into the action of the lambda model, we obtain a sigma model with a target space metric that corresponds to that of a deformed three-sphere. As you can see here from the line element, when lambda equals 0, this reduces to the line element of a round three-sphere. And notice that from the definition of the function lambda here, the definition of the delta function here, delta takes the value 1 when lambda equals 0. Also, S2 here refers to the round sphere, which is parameterized by the angles beta and the gamma. The lambda-deformed model also admits an antisymmetric field, and this is expressed by the two-form B here. This is written in terms of a volume form, of the volume form on the two-sphere, and when lambda equals 0, its field strength is proportional to the volume form of the undeformed round three-sphere. On top, we have a scalar phi, which is obtained by integrating out the gauge fields in the gauging procedure for the lambda model, and it is related to the function delta, as you can see in this expression here at the bottom of the slide. After this introduction to the lambda model, I would like to discuss some questions in the rest of my talk. The main motivation of this work is to make contact of the lambda deformations with the ideas of holography. And in order to in order to provide more paradigms of the adhesive correspondence. This requires that we promote the lambda model, the lambda-deformed sigma models into full solutions of type 2 supergravity. And this has been done in various papers in the past, such as the ones that I mentioned here in red. Nevertheless, all of them refer to lambda deformations of coset CFTs, and their embeddings to supergravity are possibly non-supersymmetric. Therefore, one of the questions that I would like to ask here is whether we can embed lambda models based on groups now in type 2 supergravity. And if this is possible, a natural question that arises is whether these embeddings preserve supersymmetry. Let me now move to the supersymmetric embeddings of lambda models in type 2 supergravity, starting with the one that was found in this paper here. The idea is to promote lambda models based on SL2R and 2 copies of SU2 to a full solution of type 2 supergravity. And the picture that I have in mind is the following. In the absence of deformation, which is when lambda equals 0, we should recover the Vezo-Mino-Witten model on SL2R and 2 copies of Vezo-Mino-Witten models on SU2. Type 2 background with such an interpretation corresponds to the near horizon limit of the NS1, NS5 brane intersection. And this has a geometry ADS3 times S3 times S3 times S1. It contains constant dilaton as well as Neves-Vars 3 form, whose components are the volume forms on ADS3 and the two 3 spheres. And in this case, the Ramon fluxes are trivial. So this setup that I just mentioned is shown here in the upper left corner of this figure. And however, my starting point will be the S-dual of this setup, which describes now the near horizon limit of the D1, D5, D5 brane intersection. And it accommodates the principal chiral models on SL2R and 2 copies of the principal chiral model on SU2. This is a solution of type 2 supergravity with the same geometry. Again, dilaton is constant. Now there is a trivial Neves-Vars form and a non-trivial Ramon 3 form, which has components proportional to the volume forms on ADS3 and the volume forms on the 2 3 spheres. This setup is shown here in the upper right corner of the figure. And the non-abelian dual of this background with the non-abelian duality taking place along the ADS3 and the 2 3 spheres is a solution of the type 2A supergravity. And this has a non-constant dilaton and also non-trivial Neves-Vars Ramon fluxes. Also, the non-abelian dual background, it should be part of the deformed solution that I would like to construct, and it is shown here at the bottom of the figure. Let me now move to the construction of the deformed background, starting with the Neves-Vars sector. For this, I will need 2 copies of the SU2 lambda model, which will replace the part of the background which is associated with the 2 3 spheres, and the copy of the SL2R lambda model, which will replace the parts associated with ADS3. Notice that the lambda model based on SL2R can be obtained from the one on SU2 that we saw before in the example through this analytic continuation here. Doing such kind of replacements in the metric, we find an expression of this form, where the terms in red correspond to the deformation of ADS3, and the ones in blue to the deformation of the 2 3 spheres. Also, the coordinate omega parameterizes the circle in the 10-dimensional geometry, and the function delta tilde of alpha tilde results from the function delta of alpha after the analytic continuation here. At this point, let me make some observations regarding the geometry. The first one is that it is kind of obvious to see that when lambda equals 0, the geometry becomes that of ADS3 times S3 times S3 times S1, as we wanted from the beginning. Also, the radii L0 or L1 and L2 of the ADS3 and the 2-3 spheres are restricted according to this condition here. And this condition is necessary in order for the equation of motion to be satisfied, not only when lambda equals 0, but also when lambda is different than 0. Maybe it's good to keep this formula in mind, as I will refer to it later. The geometry of ADS3 times S3 times T4 now can be obtained by making one of the two 3 spheres flat, and this is achieved via a zooming limit. Let's say, for example, that we want to flatten the 3-sphere parameterized by alpha 2, beta 2, and gamma 2. Then in this case, one has to approach the 0 value for alpha 2 in this way here, as it is described here, by rescaling alpha 2 with respect to the radius L2, and then sending L2 to infinity at the same time. Moreover, the geometry is non-singular for the values of lambda that are in the physical range, which is between 0 and 1. Finally, although the deformation breaks the isometries of the ADS3 and the 2-3 spheres, and ADS2 together with 2-2 spheres are still present in the geometry. Now that I have told you how the deformed metric looks like, let me move to the rest of the Neves-Vars fields. Starting with the dilaton, this is simply derived by adding the contributions of the scalars for the lambda models on SL2R and SU2, which amounts to an expression of this form here. Again, the red color refers to the contribution that comes from the SL2R part, while the blue to that what comes from the 2 SU2s. It is easy to see that for lambda equals 0, each of the deltas or delta tilde are equal to 1, and therefore the dilaton is trivial. In the same way, in order to construct the Neves-Vars to form, we add the relevant pieces from the SL2R and the SU2 lambda models, and as a result, the Neves-Vars form is given in this 3-line formula here. Now, setting lambda to 0, we see that the field strength of these two forms is given in terms of the volume forms of the ADS3 and the 2-3 spheres. This completes the construction of the Neves-Vars sector, which is in agreement with the one for the near horizon limit of the NS1, NS5, NS5 setup when lambda equals 0. Moving to the Ramon sector, in order to derive it, it is convenient that we make use of this transformation rule here. In this formula, the fat F symbols refer to the Ramon polyforms for the lambda deformed background, as well as the one that arises from the near horizon limit of the D1, D5, D5 setup. Notice that the slash stands for contraction with the gamma matrices in 10 dimensions. And the two polyforms are related via multiplication with the deformed dilaton here through this exponential, and also multiplication with the inverse matrix omega, which is expressed in terms of gamma matrices, as you can see in this long expression. Also, there is a constant mu that appears in the transformation rule, which I will not present, but I can tell you that it depends exclusively on k and lambda. And in the special case when where lambda equals 0, it vanishes, leading to trivial Ramon fluxes. And this is in agreement with the solution for the near horizon limit of the NS1, NS5, NS5 setup, which has trivial Ramon sector. Moreover, the form of the matrix omega suggests that the polyform for the deformed background contains only Ramon-Ramon forms of even rank, and therefore we are talking about type 2A solution. The type 2B counterpart can be simply derived by a T-duality along the circle S1. The transformation we used to derive the Ramon-Ramon content here mimics the transformation the Ramon-Ramon fluxes under non-abelian duality, which was found by Itsios and Thompson back in 2010. Let me now move to the discussion about the amount of supersymmetry preserved by this deformed solution. And for this, all we need is to resort to the variations of dilatino and gravitino under supersymmetry in type 2A supergravity. And due to the fact that in the deformed case, the Ramon-Ramon sector is trivial, while in the presence of deformation, there are Ramon-Ramon fluxes generated, it is natural to consider the undeformed and deformed cases separately. Starting with the dilatino variation for lambda equals 0, we find that it is solved by a single projection. And this suggests that the undeformed solution preserves 16 supercharges, which is in agreement with what we know in the literature. In the deformed case, the dilatino variation is solved by imposing an additional independent projection on top of the one that we found in the undeformed case. Therefore, we expect that the deformation breaks supersymmetry by half, and the solution preserves 8 supercharges. Nevertheless, in order to verify the statement that I just made, we also have to check the gravitino variations. And indeed, it turns out that both in the undeformed and in the deformed scenario, we do not need any further projections in order to solve the gravitini. The solution for the killing spin or epsilon for any value of lambda, including the lambda equals 0 case, is given by this long expression here, where eta here is a constant spinor that satisfies the projections that are mentioned here at the bottom of the slide. Notice that the terms in the parentheses in the first equation define a projection provided that the radii L0, L1, and L2 satisfy the condition that we saw earlier, which guarantees that our background solves the supergravity equations of motion. Also, notice that the second projection is imposed only when lambda is different than 0, which confirms that the supersymmetry is broken by half in the presence of deformation. I will now move to the second example, which describes the deformation of the near horizon limit for the NS1 NS5 intersection. And this was derived in this work here. Indeed, a second supergravity background can be obtained by promoting the lambda models on SL2R and SU2 into a full solution of type 2 supergravity. And this was done along the same lines as we did in the previous example in this work here. And but there is an alternative way to derive this solution by going to the deformed solution that I presented just now and applying the zooming limit that makes one of the 2-3 spheres flat. What we find in this case is a background which interpolates now between the near horizon limit of the NS1 and NS5 intersection with geometry ADS3 times S3 times T4, and the non-abelian dual of the near horizon limit in the D1, D5 intersection. The deformation again breaks the isometries of the ADS3 and the 3 sphere, but an ADS2 and the 2-3 sphere are still present in the geometry. Also, the deformation breaks supersymmetry by half. So again, we find 16 supercharges when lambda equals 0 and 8 supercharges otherwise. Finally, this deformed background fits in a class of type 2 solutions with a part of the geometry being ADS2 times Calabi-Yau2 times Riemann surface. And this class of solutions preserves 8 supercharges and was constructed recently in a paper by Legramanti, McPherson, and Pascal. I have now arrived to the conclusions, where in this talk we saw how to promote the lambda models on SL2R times SU2 and SL2R times 2 copies of SU2 to full solutions of type 2 supergravity. In the absence of deformation, the solutions correspond to the near horizon limits of NS1 and NS5 brane intersections, while when the deformation parameter approaches the value 1, we recover the non-abelian duals for the near horizon limits of D1 and D5 brane intersections. We also saw that the deformed backgrounds maintain ADS2 and S2 factors in their geometries, and that in the absence that in the presence of deformation, both solutions preserve 8 supercharges, which is half the amount of supersymmetry preserved by the undeformed backgrounds. There are some open questions that might be interesting to address in the future, starting with a more ambitious one. This would be to check whether integrability is preserved in the presence of Ramon fluxes. And another direction that we could follow is to understand the holographic dual of the two ADS2 solutions that we just saw in this talk. And we could also study thermal effects by constructing the corresponding black holes for each of the two solutions discussed here. And finally, we could try to see whether the type 2 backgrounds admit probe branes that maintain a fraction of the supersymmetry preserved by the backgrounds. And with this, I would like to thank you for watching my video.